Okay, so I want to take a look at a P3 sample question. In this sample question, I've got a tie rod subject to an axial tensile force of 3,400 newtons. Its length is 1,120 millimeters, and it's made from circular steel of diameter 7. The question asks me to calculate direct stress, direct strain, and the change in length due to loading. For all of these type of questions, so with shear and strain, you follow a similar approach for all of them. First thing I always do is I figure out what I know and I standardize the units. Then I look at what I need to know, I look at the formulas, compare it to what I have, and see can I rearrange them to solve for what I need to know. So if I look at this question, walking through it, I have a rod with a tensile force of 3,400 newtons. So force, the unit for force is Newton, it's already in newtons, so F equals 3,400 newtons. That's okay. Our length then is equal to 1,120 millimeters. Now remember, we're engineers, we don't like that milli in front of our meter, so we convert it. Remember, milli means by 10 to the minus 3 meters. So our length in meters is 1,120 by 10 to the minus 3. If you plug that into your calculator, you're going to see that it works out as being 1.12 meters. We're told the steel is circular, so I've drawn it up here and shown us an image, and it's got a diameter of 7 millimeters. So diameter equals 7 millimeters. Hopefully we've learned our lesson from last time. We want to convert that to meters, so 7 by 10 to the power minus 3 meters. Okay, so standardize my units. What I do now is I look at what I'm looking for, I look at the formula for it and see what I know or what I need to find out. So stress is equal to force over area. The area is here, so it's going to be a circle. So area of a circle is equal to pi times r squared. So the area of that circle is going to be pi times, now I've got a question. So I know d, I know my diameter, but not my radius. But if I remember, my radius is half my diameter. My radius is equal to a half 7 by 10 to the minus 3. So I work that out. It's going to equal 3.5 by 10 to the minus 3. So area of my circle is going to be pi times 3.5 by 10 to the power minus 3 meters. My force, I know it's 3,400, so I can calculate my stress in this question. So stress equals force over area, which is equal to, change the colour of my pen, 3,400 newtons over pi times 3.5 by 10 to the minus 3 squared. That should have been squared up here too, sorry, or squared meter. It's going to work out to be a pretty big number, 8,347,233. So if I want to round that, I can call it 88.3 megapascals because it's newtons per meter squared, or I can write it as 88.3 by 10 to the power 6 pascals. But I know the stress that's happening in the system now, so I've solved question 1. Question 2, we're looking for strain. So before I do anything, I want to look at my formulas, and formulas that include strain. So strain is equal to the change in length over length. The only thing I know in this equation is I know my length. So there's two variables in it. There's the change in length, which I don't know, and strain, which I don't know. So I need to go and look at other equations that include strain. I know E, my modulus of elasticity, or Young's modulus, is equal to stress over strain. I know my stress. I don't know my strain. I need to read through my answer and see my total Young's modulus. So in the initial bit, we weren't told Young's modulus in there. But further on in the question, we are told it has a modulus of elasticity equal to 207 gigapascals. So before I do anything, 207 gigapascals equals E. I want to standardize that. I want to get rid of that G and work using pascals. To do that, it's 207. Giga means 10 to the 9, so 207 by 10 to the 9 pascals. So now I know E, I know my stress value, and I can solve for strain. So if I rearrange that formula, strain is equal to stress over E. Strain is equal to stress. We said stress was equal to, up here, 88.3 by 10 to the 6 pascals. Divide by E, 207 by 10 to the 9 pascals. Our units are going to cancel, so we look good because strain doesn't have a unit. And this should work out to be equal 0.00043, or I can rewrite this as 4.3 by 10 to the minus 4. Okay, so now I've solved for stress and strain. Questions. The final thing I'm asked to find is the change in length. So if I go back to my original formula for strain, strain is equal to change in length over length. I should be able to rearrange that to solve for the change in length. So strain is equal to delta L over L, change in length over original length. I can rearrange this. My change in length is equal to my strain times my length. So my strain value is equal to 4.3 by 10 to the power minus 4. There's no unit. My length. So my length was given to me in millimeters, 1,120 millimeters. I changed that to meters by multiplying by 10 to the minus 3. My length is 1.12 meters. 1.12. And this should be work out to equal 4.8 by 10 to the power minus 3 meters is my change in length. So I've solved these three questions. I know my stress, I know my strain, I know my change in length due to loading in this system. So this has all been a tensile system. Okay. Now I'm told in the same system the tie rod is fastened to the beam using a circular rod of diameter 9 millimeters, pressing through the tie rod end and the bracket clevis. Now if you see a clevis, just remember there's two surface areas, so I've tried to show them in red there. So the area of stress is going to experience in two places. So we're asked to find shear stress and shear strain if the pin material has a modulus of rigidity 90 gigapascals. So again, what I would do is I write down everything I know and standardize the units. So the only real thing I'm told is that I have a diameter of 9 millimeters. So it's a new diameter in this system, new diameter. Now my diameter is 9 millimeters. which is 9 by 10 to the power minus 3 meters. My radius is equal to half my diameter. It's equal to half times 9 by 10 to the power minus 3 meters. It's going to equal 4.5 by 10 to the power minus 3 meters. So now look at what I've been asked and look at the formula for it. So shear stress, it's a different symbol, but the equation is the same. So tau equals force over area. The force in my system hasn't changed. So go back to the start of this question. Force is still 3,400 newtons. So force area just need to remember it's twice the area because it's with the clevis. So area, instead of being pi r squared, it's going to be 2 pi r squared for this because of that clevis. Just remember that. So it's going to be equal to 2 times pi times r. We said it's 4.5. It's from just up there. 4.5 by 10 to the power minus 3 meters. So I know force, I know my area. I can plug in and solve for shear stress. So shear stress tau is equal to 3,400 newtons over 2 pi 4.5 by 10 to the minus 3 squared. So we're going to end up with a unit that's newtons per meter squared. It's going to be a Pascal, so I'm on track. And this will work out to equal, it's going to equal 722 311 pascals, or 26.7 megapascals, which I can rewrite as 26.7 by 10 to the 6 pascals. Second question asked me to find shear strain. So formulas I know that include shear strain. Strain equals change in length over length. Similar to the first one, I know length. I don't know what the change in length in this system is going to be. And I don't know what the strain is. That's what I've been asked to find. Other equations that use it. Your modulus of rigidity, G, is equal to shear stress over strain. I know my modulus of rigidity. I know my shear stress. I can rearrange this formula and solve for strain. So strain is going to equal stress over modulus of rigidity. All I need to do is plug it in. So stress, I've said, is equal to 26.7 by 10 to the power 6 pascals. G, my modulus of rigidity, I was told it up here, 90 gigapascals. Remember, if I have giga, it means by 10 to the 9, so 90 by 10 to the power 9, that's how I get rid of that G, pascals. And I worked this out, and it should equal 0.2966. There's no unit, so I'll round it up. 0.3. That's us done. We've solved for the 5 questions in both of these systems. The tensile system up here. So tensile. And for the shear force system down here. Shear.